Crystallography, page slide 11, three-dimensional lattice. So, this slide is all about, first of all, it's about lattice. And secondly, it is about three-dimensional lattice. Lattice, like we know, is a framework, right? How the framework of a crystal, how it's looking like, how the frame looking like, the shape that define the shape of a crystal. So three-dimensional lattice mean like an object, a solid, the framework of a solid. And in the 3D system, right, we use 3D the 3D axis ABC XYZ, that's what I mean. And XYZ, we have vectors. In X direction we have vector magnitude of A, and in Y direction we have magnitude of B, and in Z direction we have the magnitude of C. So let's say we have a 3D vector from the origin to a point that has A magnitude in X direction, Y magnitude in Z direction, and C magnitude in the Z direction. And this vector, we call it lattice translational vector. Why do we call it lattice translational vector? Because this vector is why is it calling a lattice vector? Because this vector is being drawn in the framework, using the framework of the lattice, right, from the origin point to a point in space. And this lattice, it has we define a three-dimensional axis in this lattice. We define where the origin should be, and what is X direction, what is Y direction, and what is Z direction. And we define what are the unit, what is a unit vector for each of the direction. That's why we call it lattice vector. Why is it calling lattice translational vector? Because all vector or any vector can be translated in the tree, can be translated. That's what it means. It can be shift to the right, shift to the left, shift down, shift up, anywhere. That's why it is called translational vector. And lattice translational vector, it just means that a vector is being drawn, is being defined in the lattice, in the framework of a crystal. So, and that's what it means in slide 11. Slide 12 on unit cell and primitive cell. A unit cell is the smallest repeat entities in crystal which reflect the highest possible symmetry. The smallest repeat entities in crystal Smaller rip. Well, it is often in a box shape, right? Box means square with all size equal, and all angle are being 90 degree. Primitive cell is the smallest repeat entity with minimum volume or area, meaning that this is the smallest the smallest repeat entity with the smallest volume. The smallest volume it's for two-dimensional pattern, and it is often a parallel path. So minimum volume, primitive cell is minimum volume, smallest minimum volume unit cell. Unit cell is the basic and smallest and repeat entities in a crystal, and primitive cell is the smallest repeat entity with the smallest volume. Of course, everything is in 3D, and primitive cell, of course, is always smaller than unit cell in both 2D area or 3D volume. The primitive cell often is the parallel path with 6 surfaces like any box shape, 12 edge like any box shape, and 8 corners like any box shape. That A could be smaller than B, and C could be the biggest side, the largest side. And triangle, alpha, beta, gamma, they could be different. They could be the same, and they could be different. Alpha is the angle between C and B. Beta is the angle between A and C, and gamma is the angle between A and B. But it can be backward, right? Don't let it fool you. Slide 13, crystalline structures, lattice and basis. Again, structures, lattice, basis. So a structures, crystalline structures, is equal to lattice plus basis. A structures is always equal to lattice plus basis. Lattice again is a framework, the shape of a structures. It defines the shape of a structures, the bone, the framework, and basis or element or atoms or the muscle that being built on the bone, the framework. You must have a structures before you have anything else, any elements, further element. So in our case, let's say for silver is BCC. The framework, the lattice is the BCC, and the basis is the silver element or silver atom. Same for anything else. And for slide 14, CSCL, we have cubic lattice point. CSCL is like NaCl. It is a body center cubic. It has body center cubic structures. And so the lattice point is a cubic lattice point. So a box shape, right? The framework is a box shape with vectors of U, A, V, B, W, C's. And the bases are black atom and red atom, where black atoms are chloride and black and red atom is CS. The translational lattice vectors in the framework is defined by as vector R, big capital R, UVW is equal to U magnitude in the A direction plus V magnitude in the B direction and W magnitude in the C direction. And the basic vectors is defined as vectors little r with x magnitude in the A direction and y magnitude in the B direction and z magnitude in the C direction, where x, y, z less than 1 but bigger than 0. For diamond structures, right? Diamond structures is a complex structures, requires a complex structures. The lattice, of course, is it had a box shape, so it's called cubic P lattice point. And the basis is the green atom, 4 green atoms with 1 red atom and 4 orange atom with 1 green atoms. I actually don't remember what Dr. Sun said in this slide 15. I need to review what he said on slide 15. I'll put a star right here. Actually, I put a big R, so I remember that I need to review this slide. Okay, on slide 16, symmetry. There are 1, 2, 3, 4, 5, 6, 7 different types of symmetry. The first symmetry is translation. What it means is imagine a train, right? A train is I'm not sure if we should call it a vehicle, but it's imagine many rectangular box with same shape and same structure, same look, same color being moving on the railroad. Let's say you stand at location A, and you just looking forward this way. You will see that the train passing by, and notice that each block is similar. It's all the same. You see block A passing by, box B, box 2 passing by, box 3, box 4, box 5, and box number 6. Each of them keep passing by you. So that what is mean translation. Now let's go to rotation. Rotation, let's say you are standing wherever you want to stand. Let's say you are standing at never ever sail weed. So it's northeast, right? Northeast direction. And you see, let's say you are in the park and you are watching people playing what is it? I don't know what it is. But basically you are sitting, your brother or your sister being sit here on the little horse, and it's rotate every single time he passing by you. You want to wave him one time. So imagine that you have 5 friends and plus your brother. Well, 4 friends plus your brother, so 5. Each of them rotate passing by you. So you see each of them for each turn at each of the every 30 seconds in a circular motion. That's what rotation means. Rotation. And reflection. Imagine you are standing right here, and this is a mirror, right? You will exactly see yourself within about the same distance. A person in the mirror about the same distance from the mirror to you, or you to the mirror, doing the same action as you do. Whatever it is, that's reflection. Exactly same in the other direction, in the opposite direction. Inversion in 3D is mean, well, it looking like this is a it's reflection, but it's not, but in the sense of direction, in the sense of consisting direction. What it means is this. Let's say in this atom right here, we call this A, we call this B, and we call this C. A gonna be like this, C gonna be like this, and B gonna be like this. That's what inversion. So what inversion mean is you will need to define a mirror, right? And then first of all you reflect it, and then you rotate it, so like this, and then you're gonna do this and do this. So do this and do this, and do this, and so do this and do this. So what it means is you reflected, not 2D but 3D. You reflect it in the 3D sense. What it means is inversion. What inversion means is a 3D reflection. And what rotate inversion mean is rotate inversion. So not only it rotate but also being inverse. Again, inverse is 3D reflection. So this one mean here and here. So it's gonna be here and here. And then this one gonna be here and here and here. And it's gonna be here. I'm not sure about rotate inversion. Let me look around. Okay, so back to inversion a little bit. First of all, inversion means taking the reciprocal. In mathematics, it means taking the reciprocal, meaning that let's say a point is x, then the inversion of x is 1 over x. And in crystallography, or crystal structures, inversion mean that let's say if a point has x has a location of x, y, z, then the new location of that point, of a similar point, or that point is negative x, negative y, and negative z. So let's say point A has a direction of 1x, 2y, 3z. Then the new, then there will be a point similar to point A with a location of a negative 1x, negative 2y, and negative 2z. And rotate inversion in crystallography, it means it combines rotation and inversion. So that what it means is we actually rotate the object around axis, and then we inverse it. So let's say point X right here, we are going to rotate it first, and then let's say rotate it 90 degrees. So that is the new location, right? Let's say point A with one, of course, 1x location of 1x, 2y, 3z, and then we rotate 90 degrees, right? About an axis. Let's say rotate about the x-axis 90 degree. So about xy 90 degree. So that means the new location right now is 1x plus 90 degree, 2z plus 90 degree plus z. And then if we inverse the result as of for the inversion, then that's gonna be negative 1 negative of the x plus 90 degree, and the negative of y plus 90 degree, and negative z. That's a new point. And for glide in reflection, of course, glide reflection is just, first of all, we reflect the point. Let's say point A, we reflect it, and then that reflection being glide or being shipped of a magnitude somewhere. So that what the glide direction, what glide direction mean. What it means is, imagine a stair. Imagine you draw a stair that you don't want to invest to. You make a custom stair. You don't want to make a regular stair with two sticks on the side and a few horizontal stick at a step. Now you make a stair with a single vertical pole with multiple step on the side. But step 1 gonna be on the left at 1 unit up from the ground, and step 2 gonna be 2 unit up from the ground but on the right side. And then step 3 gonna be on the left, 3 unit up from the ground on the left side, and step 4 gonna be on the right side of the vertical pole but is 4 unit up from the ground. That's what is glide direction mean. And what screw axis, I'm actually not sure about the screw axis, but look closely, we can see that, let's say character A is being spaced in the A direction, and it'll be 3 times. So character B is also being spaced in A direction about 3 times, and character C being the same. So let me pull out a concrete a definition of screw axis symmetry, so I can read it out loud. So the definition that I have for screw axis is: a screw axis is a symmetry operation in crystallography that combines rotation about an axis and translation along that axis. So instead of just rotating a crystal structure, you also shift it, translate by some fraction of the unit cell length along the same axis. So rotation and translation along that axis. Rotation and translation. So instead of just rotating the crystal structures, you also shift it by some fraction of the unit cell length along the same axis. For example, to rotate 180 degree and translate half of the lattice parameter along the axis. 1 rotate. Why it matters? Screw axis are one of the non-symmetric symmetry element. So basically, rotate and translate. Rotate then translate. Say we rotate. Oh, I see what it means. What it means, rotate and translate, is, imagine a screw, right? The more you rotate, the more you screw or you unscrew, the screw gonna go up or go down. So let's say this screw right here, it has A, B, and C. So if you go in the clockwise direction and you start with A, then it will go to B, and then it go to C. So what it means is A, B, C, A, B, C, A, B, C. That's a rotation. For each rotation, A, B, C keep appearing. But it's also translate because it has to go up. So A, B, C, A, B, C, A, B, C. It has to take turn in that way. Go, translate, and rotate. Now we go to slide 17, symmetry operation. So this slide pretty much similar to slide 16. It shows that translation, well, one example is starting number 5, starting here at this point, the origin, and then we translate it, let's say southeast direction, right? 5. And then rotation, of course, this number 5 being rotate from the southwest, southeast to north direction. Of course, the 5 letters gonna be writing in the way of the origin toward the direction is being pointed to. The origin of number 5 is always defined by the origin of the axis of rotation, and the pointing direction is always to the direction it's being rotated. And reflection, of course, you have to write number 5 backward as you see in the mirror. If you show number 5 in front of the mirror, the number 5 in the mirror, of course, it's gonna be in a different direction. And now, inversion, for you to invert something again, you have to, inversion mean you put a negative. In crystallography, it means you put a negative. So if number 5 is being right in from the up, from north to south direction, then now you will have to write number 5 in the north, south to north direction. In the north, so that 5 gonna be upside down. And rotate inversion, like I said, you rotate and then you invert it. So this number 5 right here, when you rotate it, right? Number 5 gonna be like this. Gonna be like this, and then you invert it, and then you invert it. So you rotate it, and then you invert it. Rotate and invert. What rotate and invert mean is you are going to, this is inversion right here. You put inversion to it, but then you rotate it. This is invert, and then you rotate. So if you rotate, and then you invert, it's gonna be the same, right? If you're gonna be, yeah. And then you're gonna invert it. Invert it mean here. That's it. So rotate and invert. You can do rotate first and invert later, or invert first and then rotate. You can do any of the step in rotate inversion firstly. Any of the step can be done firstly in rotate inversion. Similarly, glide in reflection. Well, if you reflect it and then you glide it, that's gonna be similar as glide and then inversion in reflection. Why? Because let's say you glide and then you reflect, or you reflect and then you glide, same. Any of the step can be done firstly, but just make sure you know which one is the origin and then which one is the first generation, the first glide reflection, and the second glide reflection. And for screw, you need to know what is A, what is B, what is C, like for every 90-degree rectangular. So let's say A gonna be 5, and then B is gonna be of course 5, and then C is gonna be here. So next one gonna be here. But like rotate and then screw is rotate and then glide, rotate and translate. So you rotate, you translate, you rotate, you translate, and then you rotate. You rotate, you translate, and then you rotate, and you translate. And then you rotate, and you translate. Alright, slide 18 is about rotational symmetry of individual pattern. Rotational symmetry of individual pattern. What it say is that so rotational symmetry again is, let's say you have your origin and then this is A, you're gonna rotate this A. That's what rotational symmetry means. And of individual pattern meaning that's just an A. You only have one pattern, and it's like this. Five-fold symmetry meaning it will have 5A letter. 1, 2, 3, 4, 5. 5A letters at same angle of rotation. And A-fold just mean A, letter A. So 1A, 2A, 3A, 4A, 5A, 6A, 7A, and 8A. 12-fold, I'm not gonna do the math again. Lattice has to have translational symmetry. So all lattice or the framework, it must have translational symmetry, right? Or otherwise you cannot build it. Let's draw our box lattice. So cubic lattice, right? It's like this. This is the base, so it is still a lattice, and this is the lattice. And you see, this. It must have translational lattice. Okay. 2, 3, 4, and 6 translational symmetry only. What that means is translational 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 dividing by 2 is 6. 6 dividing by 2 is 3. 3. And then if you have an other pattern, I'm not sure about 2, 3, 4, 6 translational symmetry. So I'm going to put a review here to review what he said about it. I'm going to put a big letter R so I remember that I need to review this step on slide 18. So on slide 19, why there is no 5-fold symmetric lattice? Why there is no 5-fold symmetric lattice? 5-fold. We have 5 folds. On slide 18, we have 5-fold symmetry definition. The definition of 5-fold symmetry is mean 5 letter A. 8-fold, 12-fold. Oh, so rotational symmetry of So this is rotational symmetry, 5-fold rotational symmetry. On slide 18 again, 5-fold is 5-fold rotational symmetry. But it also say that lattice has to have translational symmetry. And it also say that 2, 3, 4, and 6 for translational symmetry only. So these two statements are two different things. So and on slide 19, why there is no 5-fold symmetric lattice? Are you saying that there is no 5-fold translational lattice. Okay, so it's a lattice has to have translational symmetry. Agree. So this is sixfold right here. Why is it sixfold? 1, 2, 3, 4, 5, 6. 1, 2, 1, 2, 3, 4, 5. How do you define sixfold? 1, 2, 3, 4. I don't understand. Distance between point 3 and 4. D equal to A. What exactly does that mean? 1, 2, 3, 4, 5. This is sixfold symmetry. Okay, 1, 2, 4-fold. 1, 2, 3, 4. Fivefold. 1, 2, 3. There is no fivefold because distance between point 3 and 4 is 0.3a. 2a. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. There is no fivefold because the distance cannot be less 0.3a. I'm not sure. About slide 19. So this is twofold. 1, 2, twofold. Sixfold. Oh, okay. So for translational symmetry, right? The fold is being defined by a point. Like let's say a line had to have 2 points to define a line. So twofold. And fourfold is like a box. It needs to have 4 points to define a box. And fivefold, you cannot make fivefold. You cannot make fivefold because you cannot make a 5 point. Think about it. It's not right. Fivefold symmetry. It's a symmetry. Now it's not symmetry. 1, 2, 3, 4, 5. It's not symmetry. Exactly. It's not symmetry. Why? Because look, it's not symmetry. It's not symmetry because 5 cannot make a symmetry. This is a symmetry. But this is a symmetry. But this is not. This is a 4. 4 is like this. So if, let's say, you cannot have 1, right? Think about it. So you can, one fold, that's not a symmetry. 1 is not a symmetry. Not a symmetry right here. This is the odd one, right? So 1. So 2. Twofold. And then 3. How do you draw a threefold? Oh, threefold. This is a threefold. This is a threefold. Symmetry. Fourfold. This by definition is fourfold. And fivefold. Now, this is sixfold. 1, 2, 3, 4, 5. I know, but it's 6. You combine this, and this is 6. Right, sixfold. You cannot draw a fivefold. You can draw a 4, but this is not a 4. This is like a 4, but it's not. It cannot be a 4 because it's less than this. So it's not a fivefold. So there are only 6 fold. 1 is not a fold. 2 is a fold. 3 is a fold. 4 is a fold. 6 is a fold, but 5 is not. Because you cannot draw a 5. You cannot draw a 5. Let's say you draw it like this, right? Then this is not a symmetry. This is not a symmetry. Again, this is not a symmetry. You cannot use this, and you cannot use this as a 5 for, because clearly they are 4, and 4 is this. You cannot draw it less than this. And 5, you can just cannot draw a 5. And if this cannot be, then this cannot be. So this is a 6. By definition, it's a 6. Okay? Well, this is the definition. This is the definition. It's the definition. We gotta go by the definition. So, slide 20, two-dimensional lattice. So we study three-dimensional lattice as a box. That's a box framework, right? Box shape. Now we study two-dimensional lattice. So two-dimensional lattice. See about this twofold. Lattice. Well, two-dimensional lattice. It doesn't have to be always a conventional box shape, a perfect box shape, right? It can be a column being with a certain angle, right? This is a perfect rectangular box. There is a super neat box. There is a BCC box, and there is a BCC box. So let's talk about a box that has twofold where angle A, length A less than length B, with an where A and B has angle alpha, where alpha is less than 90 degrees, right? So that obviously, so if A less than B, let's say this, A less than B, and there is an angle between them, so that means you are drawing like this, right? And then less than 90 degrees, so it's going to be like this. And then A is not equal to B. A less than B, and A and B form a 90 degrees, so of course it's going to be like this. And A is equal to B, and A and B has a 90 degree, so that means like this, right? A and B. How many steps? I'll just draw a small step. First step first, twofold, right? So not like this, and like this, and like this. A equal to B and AB 90 degree, and then this is A equal to B at an angle, so that means like this, equal but like 60 degree. Sixfold. Why we call it sixfold? 1, 2, 3. Six again. Six mean 1, 2, 3, 4, 5, 6. Twofold mean 1, 2, 1, 2, 1, 2, 1, 2, but like this, 1, 2, being at angle. A and B form an angle, right? And then twofold is like this, but it's also share an angle. Fourfold. Why is it fourfold? So fourfold is A and B. Fourfold is A and B like this. Fourfold is A and B like this. Fourfold is A and B like this. And then sigfold is like this, where A equal to B, but at an angle of 60 degrees. And A not equal to B is also twofold. A not equal to B, yeah, this is A and this is B, not equal to B. Alpha is 90 degrees. So that means like this. Oh, A is B. Okay. Wait, so that means twofold. A, B, alpha is 90 degrees. Yeah. So what is the difference? Hey, I don't quite. Twofold A not equal to B and alpha equal to 90 degree are exactly the same like this. It's just that there is a interstitial being put in the middle of each of the lattice to form a BCC structures. I'm gonna put a review here so I can read it again and over again. Okay? Hold on.